So the question here is 114.4, which is the swimming with the shark problem. So first, the problem is two people can choose either to swim or not swim on the first day. On the second day, they will choose to not swim and not swim as well, but then that decision is fixed, so I don't need to worry about the second day. So if they have high probability of meeting a shark, so I'll draw it like this. No, that's not a shark, but yeah, so if they meet a shark with probability pi, they get utility minus c. If they stay out, they get 0. If they swim and not meet a shark, then I get utility 1. So there are 2 days. So if on the first day they don't meet a shark, then on the second day they will get another 1. So that's how to write down the utility function. And so there are pi probability that I get minus c, plus there is 1 minus pi probability that I get to swim with utility 1, plus on the second day I'll swim as well because I know that there are no sharks. And similarly, I think we get the same thing with this. So it doesn't really depend on what the other person do. If I don't swim, then there is pi probability that I don't get anything, because if there are sharks, then tomorrow I won't swim as well, so I will get 0. And there's 1 minus pi probability that I only get 1, because I didn't swim on the first day, so I only get 1 from the second day. And similarly, if both of us don't swim, then on the second day we face the same problem, so we basically have the max between this expected utility, this thing times 1 and 0. So basically on the second day we will make the same decision. If this number is larger than 0, then we will go swim on the second day. And this is I will not swim on second day. So that's how to formulate this problem. And then if you have this, then I think solving is very easy. You don't even need to write down the other guy's utility because it's symmetric. So I'll have alpha and 1 minus alpha here. The purpose is making s indifferent to n. So the indifference condition is the first thing multiplied by alpha plus the second thing multiplied by 1 minus alpha, which they are the same. So I'll just write it once and also simplify this. And this needs to be equal to alpha times the first one plus 1 minus alpha plus 1 minus alpha times the max of these two. So I guess I will do the 0 one first because it's easier. So in this case, we want 0 to be larger than or equal to this. Then the max between these two will be 0. Then we solve this thing. This becomes alpha is equal to 2 minus pi c over 1 minus alpha. I mean, not alpha, 1 minus pi. So note that if you rearrange this, you get pi c is larger than or equal to 1 minus pi. So this expression is larger than 1, so it's actually okay. As long as this number is smaller than 2, then this is a mixed Schrödinger equilibrium. So before we do the other one where the max is the other thing, we can take a look at the utility. So if the max, so let's use another pen. So if the max is this thing, then this for sure is smaller than this, because there's 2 here, it's only 1 here, so this number is always larger. And also, if we are comparing these two, we know from the fact that this is larger than 0 means this thing is larger than or equal to 0. So if we move the alpha c to the pi c, no, not alpha, to this side, then we know that this number is larger than pi c, so this term is larger than 0, and this term is equal here. Let me rephrase this. So we basically have this thing plus 1 minus pi plus another 1 minus pi, and 1 minus pi is equal to 1 minus pi. This number according to this inequality, this number is larger than 0. So again, this thing is larger. So what it says is basically, if this expression is larger than 0, then S is always preferred to N. So we have a dominant strategy. Then we don't have a mixed strategy. So in the other case, so we want to say if 0 is smaller or equal to this, then there is no mixed strategy match. So we only have this one. And the condition we have is this.